Hi again. In the previous video, we saw how to use futures and the asynchronous iteration protocol to wait for data to process. In this video, we'll take a look at more ways to share data between tasks and synchronize their operations. The async.io package provides lock, semaphore, event, and condition classes that are pretty similar to the ones we looked at in the context of concurrent.futures. They provide the same method names and fulfill the same roles. The important difference is that for async.io's versions, some of the methods are coroutines, and some are not. Specifically, in each case, the acquire and wait methods, if they exist, are coroutines that must be called by a wait. This is because they need to be able to pause until some specific thing happens. And only a coroutine can pause and hand off control to the scheduler. Having mentioned lock and the rest, I want to point out that while they are sometimes necessary, they are less often needed under async.io than they would be in concurrent.futures or other systems which provide multiple streams of execution. That's because async.io scheduling is cooperative. It's only possible to switch between execution streams at await expressions, which means that if there are no awaits within a critical section of code, it can't be interrupted. No other task can modify the same data at the same time because no other task has an opportunity to run any code during that time. Thus, lock and such are only needed when a critical section of code does in fact use await at least once. We've seen as completed and wait functions before in concurrent.futures. Async.io's versions are coroutines because they too need to suspend until it's time to continue executing. But they're not much different in how we use them. The wait coroutine still waits for a group of futures to end, with an optional timeout, and returns a list of the futures that are ready and a list of futures that are not ready when the time expires. The asCompleted function still takes a list of futures and produces futures of the results in the order that the results become available. Then we extract the actual values from the futures with await and are good to go. In this code, there's no telling what order the results will become available, but each time a value does become available, it gets printed. Async.io provides some other interesting coroutines for collecting data from futures, particularly wait for and gather. The wait for coroutine lets us wait for another coroutine to finish, but with a timeout. The first two coroutines in this example do the same thing, except that if foo doesn't finish within 5 seconds, the second version will raise an async.io timeout error. In the third code block, we're still doing the same thing, except if foo times out, we print a message. Then there's the gather coroutine. What it does is take a bunch of futures and make a single future that will be done when all the sub-futures are done, and result in a list of the sub-futures results. There are a bunch of uses for something like that. But one very nice thing we can do with it is use it to construct the future that we pass into run_until_complete. In effect, we're telling async.io that it should run until all these futures are complete. Futures are great for communicating a one-off value between tasks, and event objects are good for sending simple signals. But sometimes we want a more fully featured communication channel. Fortunately, async.io provides us with a queue class and a few variants based on it. Async.io's queue has both the put and the get methods as coroutines. So, we need to call them with await. And we have to already be in a coroutine to call them, unless we were to actually use the ensure future function to launch them as separate tasks. However, the queue class also has methods called put no wait and get no wait that are not coroutines and can be called from anywhere. That makes the queue class quite useful for communicating new data into a system of coroutines, as well as sending data between coroutine tasks. Async I/O provides a couple of variant queue types that return their stored values in different orders. Instances of priority queue give back the smallest object they contain, according to less than comparison, when we call get or get no wait. So if a priority queue contains 34, 2, 5, and 97, calling its get coroutine would return 2. Then next time, it would return 5, then 34, then 97. A LIFO queue, on the other hand, always gives back the most recently added object. It is, in other words, a stack data structure. Async I/O also provides a joinable queue class, which adds an extra join coroutine and a method called task done. With a little bit of extra work, using a joinable queue allows coroutines to pause and wait until the queue has been emptied. In this video, we looked at tools that we can use to transmit data to and from asynchronous coroutine tasks, and force synchronization on them when necessary. In the next video, we're going to see about using async I/O and coroutines to write a client-server program that communicates over the network.